All right, friends, so our goal for these set of notes is to be able to find the area under the normal curve. So let's take a look at our first example here. Math section of the SAT are scaled so that the scores roughly follow a normal distribution with a normal distribution with a mean of 500 and a standard deviation of 100. Jane scored 600. We want to know what was her percentile. Well, what is a percentile? So a percentile is equal to the probability or the percentage that are less than a given value. So we're looking for this. Now this is our first introduction to a probability statement. So what a probability statement is letting the reader know that you're looking for a probability. So this P here represents the probability. We're looking for the probability that a value, in this case an SAT math score, is less than 600. This is a really, really powerful tool that we'll be using throughout this class. Being able to read through a problem and figure out what the probability statement is for it can be extremely helpful as we work through this class. So whenever you see percentile, we know that we're looking for the probability that an x value is less than something. In this case, 600. So in order to find this, we're going to draw out our normal curve with our mean of 500, go 3 standard deviations above and 3 standard deviations below, and we're going to try to shade the region that we are trying to find. So we're looking for the probability that we're less than 600, so we'll shade less than 600. Now the one thing I didn't include on this was a label for my axis, so it should say SAT math scores is what we're plotting here since we're using real data, but I know you all did that and were yelling at me as you were watching the video. So in order to find this area, we can use this formula right here. Now, if you haven't taken calculus, and maybe even if you haven't taken BC calculus, then this is probably going to look a little bit weird for you. So there's got to be an easier way than this, because calculus isn't required for this course, and there is. We can use something called the empirical rule. Well, the empirical rule is sometimes called the 68-95-99.7 rule. And that's because if we go from one standard deviation to the left to one standard deviation to the right of a normal curve, we can find about 68% of our data. Between 2 standard deviations, we find that about 95% of our data can be found. And for 3 standard deviations, 99.7% of our data goes from 3 standard deviations to the left to 3 standard deviations to the right of the mean. Well, let's break it down even further. If 68 falls between -1 and 1 standard deviation, then how about from the mean to 1 standard deviation? Well, that's going to be 34%. And if 95% fall within 2 standard deviations, what percent will fall between 1 standard deviation and 2 standard deviation? How about just this region right here, or just this region right here? Remember, it's symmetric. Well, that would be 13.5. For 3 standard deviations, or between 2 and 3 standard deviations, we find that it's 2.35% of our data. And beyond 3 standard deviations, we find that it's 0.15% of our data. Okay? So that's 0.0015 if you're writing it as a decimal. So in order for us to find the probability that x is less than 600, well, we can use that empirical rule to approximate it, right? We have our 34% plus our 34% plus our 13.5% plus our 2.35% plus our 0.15%. Or there's a quicker way to do this. Well, we know this is symmetric, so we know 50% of our data is less than the mean. We could add 34% to this 50% and find that our answer is 84%, putting her in the 84th percentile. Okay. So take a moment pause the video and sketch each of these. Now, I'm not going to put the answers to these up there, so you'll have to check with your partner. Make sure you are shading the area. And see if you can find these probabilities as well on your own. This is something that you can do in your class or share your answers with your classmates. All right, now let's talk about something pretty interesting. How would our box plot fall within our not standard normal curve, in any normal curve? Well, we know that 50% of our data is between Q1 and Q3, and 68% of our data is between one standard deviation to the left and one standard deviation to the right. So that means that Q1 and Q3 fall within, are inside one standard deviation from the mean. We also can see when we calculate this out that Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR are not quite to 3 standard deviations to the left and 3 standard deviations to the right of the mean. So therefore, any value that is 3 standard deviations to the left or to the right or beyond that would be considered an outlier. Now, we can actually find percentiles also by converting actual data values into z-scores. So, Travel and Leisure magazine is running an article about the worst airports in the country. Of all the airports in the country, big and small, the average delay time, so this is the mean for the entire population, is 41.7 minutes with a standard deviation of 10.8 minutes. We want to find the proportion of airports that have a shorter average delay than Philadelphia's airport and DCA's airport. So Philadelphia's is 74.1, while DCA's is 20.1. To calculate our z-score, we can use our z-score formula by taking this value, subtracting it by the mean, and dividing it by the standard deviation, giving us a value of 3. For DCA, when we do that same formula, we find that it's -2. So for Philadelphia, we're trying to find the probability that a airport delay time, x being an airport delay time, is less than 74.1, or if we write it as a z-score, we can find the probability that a z-score is less than 3. Now, I'm going to repeat this quite a few times this year, but one of the important things to note is if you do use x here in your probability statement, you need to define what x is. So x is the mean delay time of airports, right? Of the airport. So we could add all of these together, or again, try to find some shortcuts using our 50% as a shortcut here. And we find that 99.85% of airports have a shorter delay time than Philadelphia. For DCA, we're 2 standard deviations to the left. We're trying to find the probability that an airport delay time is less than 20.1, or the probability that a z-score is less than -2. We can sum up those two values and see that it's just 2.5%. So that's going to be the 3rd percentile and the 99th percentile. We never do 100th percentile, and we never do 0th percentile. So which one would be better in this case? Well, 99%, or the 99th percentile, means 99% of airports have delays that are equal to or shorter than the airport in discussion, while the 3rd percentile means that 3% of airports have delays that are equal to or shorter than the airport in discussion. So the 3rd percentile would be best, right? Not many airports have a shorter delay. So I know we're used to seeing percentiles in terms of test scores, and so in those cases, we want a high percentile. That means that 99% of people scored less than us, but there are some circumstances where a lower percentile is better. All right, little information about Mr. Whitesell. So, my cousin, and he's going to kill me especially for posting this online, but my cousin Adam was quite short for his age when he was younger. This is Adam right here. This is actually my family. That's me. That's my sister. That's my brother-in-law. And these are all my cousins. Not all of them. These are many of my cousins. But this is Adam. So in the 6th grade, Adam was only 47 inches tall. We want to find his z-score and his percentile. So the heights of 11-year-old boys are normally distributed. The average 11-year-old boy was 52 inches with a standard deviation of 2.5. So the first thing we'll do is calculate Adam's z-score by plugging in all of those values, and we find that Adam is 2 standard deviations below the mean of heights of 11-year-old boys. So we can shade that using the probability that an 11-year-old boy would be less than 47 inches, or we can use our z-score, the probability that a z-score is less than -2. So there's Adam. We can add those values up, and we find that Adam is only taller than 2.5% of 11-year-old boys when he was 11 years old, meaning that he's in the 3rd percentile. On the other hand, I had my friend Meredith, and she was one of the tallest people in my 6th grade class. I think she was the tallest person in my 6th grade class, but definitely one of the tallest girls. She was the tallest girl. She was 70 inches tall. We want to know what was her percentile. So for 11-year-old girls, the average is 60 inches with a standard deviation of 4 inches. So calculate her z-score, and we find that it's 2.5. Well, when I plot that, we see that we have our z-score. Here's our 2, here's our 3. We're going to go halfway in between those two. So we're looking for the probability that an 11-year-old girl is less than 70 inches, or the probability that a z-score is less than 2.5. But in this case, her z-score is not a perfect standard deviation. So how can we calculate the areas when they're not perfect? Well, can we just take half of that 2.35? Can we take half of the 2.35? Well, no. This region is slightly bigger than this region. So it's not an equal distribution to the left and the right between my standard deviations. So we can't just take half of that value. So what can we do? Well, there's 2 ways. Number 1, we could use a z-score table. Number 2, we could use a calculator. We're going to talk about how to use the z-score table first. So this is a z-score table. You should have gotten a copy of this already. On the left, we have our first 2 digits of the z-score. Up here, it's telling us that the value inside the table is representing the area to the left of our z-score. On the inside, we have those actual areas, or those actual values. And up top, we have that last digit of the z-score. So we can go to 2 decimal places when we're looking at a z-score table. So Meredith's z-score was 2.5. So we're going to go on the left down to 2.5. And if there's no digit afterwards, then we're going to go over to 0.00. And we find that Meredith's Meredith's area, or percentage below Meredith's z-score, is 99.38%. So she was taller than 99.38% of 6th grade girls, meaning she's in the 99th percentile. So, again, Meredith's taller than 99% of girls in my class. She continued to grow faster and ended up playing volleyball at the University of Maryland. Adam is, and actually not currently anymore, he did graduate, but he did wrestle at the University of Maryland. So they both ended up being athletes, and that's why I said Adam could kill me if he saw that I do this. So don't tell Adam. So, using your z-score table, let's find the probability that a z-score could be less than 0.47. Well, again, we're going to go down to 0.4 because there's no whole number there. And we're going to go across to 0.07 and find that there is 68.08% of data is below 0.47. Take a moment and see if you can calculate the rest of those. So I'll post this online. You can check it online, but I'm not going to go through it in this video. Hope you found that fun and interesting. learned a little bit more about Mr. Weitzel. Have a wonderful day.